in materials for a desired device functionality. Professor Joss will speak to us on smart sustainability, renewable materials, big data, circular one up. On behalf of the Department of Physics, I request Professor Joss to deliver the lecture. Professor Joss, thank you.
Thank you, Professor GJ. And thank you all the attendees, principal of the college, Dr. Namal John, and all the attendees. Good evening to all of you, or good afternoon. I have to find out where to share my screen so that I can show you my slides. Hello?
Hello, sir. There is a window, a tab called Present Now. You can click that Present Now.
Okay.
In the below right side, bottom right side, there is
Present Now is there.
Okay, you can click that tab.
But can you see my screen now?
No, we are seeing your video. Face only.
Okay, so there should be a share screen button which I am looking for.
Sir, first of all, you have to open the PowerPoint and keep it
is open.
An open window.
Yeah, it is open.
Then click Present Now.
Yes.
Then when it pops up, you can see a window. There are three options. And select a window.
Yeah, window, right?
Then there will be the window open. You can select that PowerPoint and then present. Click
share.
Present. Share.
So can you see? Can you see it now?
Yes, it's coming.
Okay, that's great. The screen. I hope all of you can see my screen. As Professor Jijimon has pointed out, it's about 6:30 in Malaysia. In India, it should be 4+. So what I would be speaking about today is smart sustainability, renewable materials, big data, and circular economy nexus. In this talk, I don't focus much on my past activities, which you can easily Google and find out the papers published and can read. What I am going to share with you today is what I thought is important for the future of the sustainability of the planet, and as scientists, how should we orient? So this is my team. My laboratory is Nanostructure Renewable Energy Materials Laboratory, and soon it should be renamed as Center for Sustainable Materials and Circular Economy. These are the people in my laboratory.
Sir, excuse me.
Yes.
PowerPoint is not coming here.
Hello.
So your video is coming.
The PowerPoint cannot. Meet.google.com is sharing now. In my screen, it is actually sharing.
Okay.
Is it coming now?
Hello, sir. PPT on.
We can see it.
You can see my slides, right?
Yeah. Okay.
Yes, sir, we can see that. We can see. Okay.
All right. So the top two panels are the people who graduated already, and the bottom panel are the people currently in the laboratory. So in this laboratory, we focus on energy conversion materials, mostly for solar cells, and energy storage materials, mostly batteries and supercapacitor materials for batteries and supercapacitors, and more recently on renewable materials. In our laboratory, my team has published over 215 papers, as Professor Jijimon has pointed out, which are cited over 10,000 times. And we filed 10 patents and sealed 2 patents we have generated 4 million ringgit Malaysia research grants, nearly about 1 million USD. And we are partnering, we are not working alone, we are partnering with top-ranked universities and industries in the US and Canada, Europe, Japan, Korea, Singapore, Taiwan, India, and China. So to show you what has significantly happened in my laboratory is we have been working on different types of materials, as I have pointed out, for two applications. One is energy conversion by means of solar cells, and the other is energy storage materials for batteries and supercapacitors. There we developed materials in diverse morphologies like nanowires, nanofibers, composites, nano and microcubes, nanoflowers, and so on, a variety of materials. And two significant discoveries in my laboratory is a nanomaterial supporting band-edge type electron diffusion, and the other one is band-edge type electron diffusion in nanostructured material that is very important in the context of nano photovoltaics. And the other one is a material that can simultaneously support high power density and high energy density in supercapacitors and batteries. The right panel shows two significant devices that we have developed in the past. One is the world's first nano road solar module with efficiency about 15%. That was a module with efficiency 15%, which received a gold medal for engineering excellence in INPEX, United States of America, in 2016. And what you see in the bottom panel is a 6 volts, 75 farad supercapacitor with a power density about 5,000 watt per hour. And we received a gold medal as well as Invention of the Year award from the British Invention Show in London in 2015. So these are actually excellent performance indicators, probably you would think. And with these discoveries, we have approached many companies, industries around the planet to commercialize them. Then we realized the real difficulties of commercializing a research product. I hope you can see this graph. And this is the industry, how industry perceive with the university scale inventions. What you see there is a graph where the y-axis shows the cumulative profits or loss, means investment of money. And what is in the y-x-axis is time. So at time t is equal to 0, we conceive an idea and start doing research. And you would see that at the beginning of the research, we don't require enough investments. See, with a little investment, we will develop a prototype, or we will prove our concept. Then we go on to develop a prototype at the development stage, where we will transfer the technology to a company. Now, look at the investment required for a company to make this product to be commercialized and make a profit. You would see that much more is required to commercialize or make this device in the public domain. And it leads to a place called the valley of death, and that lay in between the product launch and the success as a new product is a time of frustration in technology. This is called trough of disillusionment. And that leads us to the valley of death. And most of our university level technologies die at this valley of death. And if somebody can survive this valley of death, they move on and to meet the time axis again at the success as a business. then onwards they make a profit. So our problem, the product developed in our laboratory, when we approach this company and when we compare our product with this graph, we can identify two things. One is our materials are very specialty materials. Of course, they provide excellent properties, but they are too expensive, so that the industry cannot afford or the public cannot afford to buy it. So if the public cannot afford to buy it, no industry will be ready to invest on such technology. The next thing is the sustainability. It comes with the life cycle assessment of the product. And when we do that, we can see that if a company is demanding 1 ton of that materials developed in my laboratory or by my team, you would see that for developing 1 ton of materials, probably I need to burn about 3 tons of polymers, and that are a huge environmental load. So high carbon load and high cost of materials actually block those technologies, those really exciting developments in our laboratory to go to the commercialization. To see things more closely, look at this slide. And what is actually the problem in the coming world with the current way of thinking and materials development? We can say a lot of stories regarding how materials transformed human life in the planet. Every aspect of the modernization comes with new and innovative materials. And somebody is often said that materials are the index of human progress. Indeed, yes. See, most of these specialty materials like metals, alloys, metal oxides, ceramics, they come from the earth. When you look at this picture shown here on the right, you will see that to get this material, we need to mine them. Whether it is metals, metal oxides, ceramics, or whatever it is, if it contains a metal, we need to mine them. And if we mine them, we take the groundwater level down and down. And mining is so severe. I cited few examples here. For example, over 160 million tons of bauxite is mined every single year. Over 1 million metric ton of silicon is mined every single year. And in the US alone, 625,000 metric ton silicon was processed only in the year 2017. So when we keep going to mine our specialty material, what we do is we make our groundwater level deeper and deeper. And what it makes a situation called day zero, where your municipality or corporation tell you that, sorry, we cannot supply your water from now onwards, called the day zero. It is not a fancy. It has happened already. For example, in Cape Town in South Africa, they declared day zero in July 2017. You can see their farm. This picture in the left side is taken from a farm in Cape Town. You can see how drought they are is because overexploitation of earth resources make the groundwater level down and we cannot access them. And recently I have read that 21 Indian cities will run out of groundwater by 2020. So if we keep on mining for our specialty material, this is where we would end up, where our cities will run out of groundwater. To make things worse, human population keep on increasing. Nearly 1 billion new consumers or nearly 1 billion new population is born in every 10 to 15 years time. it can be viewed differently. But if you are a businessman, you will think that there is a billion new consumers and they need products. And if all for their products, if our resources are mined from the earth, we are going to destabilize the planet. So that's where we started rethinking of finding our materials from renewable sources. For example, how do we functionalize materials or develop materials from renewable sources? In the case of Malaysia, this oil palm plantation is the largest agricultural sector here. Malaysia is the #1 exporter of palm oil and second largest producer of oil palm. But the statistics are like, if we make 2.5 kilogram of crude palm oil, it creates 100 kilogram biomass. And usually this biomass is dumped in as landfills. Among this 100 kilogram biomass, 5 to 6% is the palm kernel shell, the hard central core inside the palm seed, just like the coconut kernel, where inside which we grate our coconuts. So this palm kernel shell has a similar central hard core inside it, which is very hard and contains a lot of lignocellulose, from where we can get starch, cellulose, and carbon. And among this 100 kilogram biomass, 20 to 25% is empty fruit bunch. So if you take the coconuts from the fruit bunch, what is left is the empty fruit bunch. That's again a great source for starch and cellulose. So how do we get materials from there is in the next few slides here. So firstly, we looked at palm kernel shell and find that it is a good source of graphitic carbon. And if we can develop graphitic carbon, we can develop graphene. And if we can develop graphene in large sheets, it solves a lot of materials issues, because graphene has been shown to be excellent materials for a variety of applications. So we started processing this palm kernel shell and looked at its crystal structure. We find that it is graphitic carbon, but the layer size is too small, like 1.5 to nearly 1.5 nanometer height, and width, the flat width is about 3 to 4 nanometer, means they are very small domains. So if there is a way to grow them into larger sheets, we can solve, but we did not solve it yet. So we derived the porous carbon from this palm kernel shell and checked the charge storage properties. When we looked at charge storage properties in a lithium half cell, and we find that it is not, you can see in the table right side showing, comparing commercial activated carbon, their capacitance and resistance. You would see that commercial activated carbon has shows nearly 50 milliampere per hour means Coulomb charge, and it has nearly 3 ohm resistance also. But when we look at palm kernel shell carbon, the charge storability is about 40% less. We get about only 30%. And that's because its resistance is very high. And we found that this resistance is coming from a large content of oxygen in this palm kernel shell carbon. So the issue is there, how do we get rid of this oxygen? There could be many chemical methods. We used 2 physical methods. The first method is heat the oxygen out. So we heat it, annealed it. So when we annealed it, you would see in that table that the capacitance, the capacity is much higher than the activated carbon, commercial activated carbon, and the resistance is much lower too. And the next thing that we did is we optically reduced them. We used a laser to laser heating to remove oxygen. And these papers are recently published in this Journal of Flavors and Compounds. You can browse it and read for details. And we further notice that even if we have a carbon performing similar or bit better than the commercial one, there contains a large passive voids in this carbon, and that do not add any functionality to the charge storage of this carbon. There, we have developed 10% metal oxides nanoflower. Means in this, we developed a composite, carbon composite, where 90% is carbon and 10% is a nanoflower. The goodness with the nanoflower is it offers numerous charge diffusion sites, so that the charge storability in the resulting composite is high. To show that, when you see, look at the graph showing in the right panel, the panel E, where the top one, the blue line, is the charge storage, the capacitive charge storage by the composite is over 500 farads per gram, one of the highest ever reported using carbon. And that is much higher than pure carbon that is shown in the bottom as the black line there. And the ceramic fillers, we used different types of ceramic. One of them is titanium dioxide. Titanium dioxide is also highly abundant in the planet. So we could, by filling these voids with ceramic nanoflowers, the voltage window means we got higher voltage than pure carbon and higher storage capability than pure carbon. We further continued this work. This is done by Binsi. Binsi is from Attingen in Quantum District, joined for PhD degree, just submitted a doctoral thesis. Continuing with this, one another work we did to functionalize them is we developed a thin metal oxide film on the porous carbon. That the schematics is shown here. So this one is the palm kernel shell, and if we conventionally heat it, we get porous carbon like what I shown in the bottom. And if we make a special processing with little amount is about 10 weight percentage metal oxide. In this case, we used manganese oxide. Manganese oxide is also highly abundant in the planet and is very cheap. So when we overcoat this metal oxide, manganese oxide, in the surface of porous carbon, we got a surface whose surface area is compared in the table right side. You would see that the surface area is of the metal oxide coated carbon is much higher than pure carbon, and their pore size is lower, so that it can accommodate charges and get it stored. This one compares the charge storability of this manganese oxide coated palm kernel shell graphitic carbon. The results are actually summarized in the table bottom. I can share this slide later so that the details you can browse it later. So you would see that, look at the table in the bottom, where the energy density and power density of pure palm kernel shell and metal oxide coated palm kernel shell is compared. Energy density refers to how much charge can be stored. Power density is how quickly it can be stored or charged or discharged. In the case of pure carbon, when we have about energy density about 8 watt-hour per kilogram, something similar or bit higher than the commercially available supercapacitors. When we have this metal oxide coated palm kernel shell carbon, you would see that the energy density increased more than 3 times higher. And what happens to the power density? power density, initially it was 6,500 watt-hour per kilogram, means that quickly it can be charged. And when you look at the power density of the metal oxide coated carbon, it did not decrease much. Usually that's the case. When the energy density is increased, power density decreased drastically. And in this case, no such drastic decrease in power density is found. So that's a good strategy. Again, if metal is inevitable, because metals offers much superior properties than bio or renewable materials. So how do we functionalize these renewable materials with minimum quantity of earthborne materials has been our focus. So this work. And in the next work, what we did is again the same, but instead of metal oxide, here we coated a metallic film on porous carbon. You would see this also done by Binzi. You would see the SEM shown here. What that's actually the microstructure of carbon containing a thin film of cobalt in this on its surface. We did a lot of characterizations to prove that we have a metal film on porous carbon. And at this moment, the paper is just communicated to a top journal of Royal Society of Chemistry. And once it is there, I will share it with you. Again, what we have seen that while doing that metal coated porous carbon, we can increase the storability and power capability of carbon electrode very significantly. So at the end of this work, what we have in our laboratory is a 3.5 volt lithium ion capacitor with cobalt coated palm kernel shell graphitic carbon, and 3.5 volts, 153 watt-hour per kilogram. 153 watt-hour per kilogram is about 60% energy capability of the present lithium-ion batteries. And when you look at the power capability, it is about 2,400 watt-hour per kilogram. That's about 10 times higher than lithium-ion battery. So while by functionalizing a renewable material means an agricultural byproduct and further processing it, value adding it, we could develop a high voltage battery that offers about 60% power capability of lithium ion battery, but 60% energy charge storability of lithium ion battery, but 10 times higher power capability of lithium ion battery. So that's the case of charge storage. Now, show you a few examples how the other waste from palm kernels or oil palm plantation can be used to make useful products. So what is shown here in this slide is the palm fruits. These are the palm fruits. From there, if the fruits is taken, you would see the empty fruit bunch. And this empty fruit bunch is again a good source of lignocellulose, from where we extracted cellulose. We extracted cellulose and developed a non-woven fibrous film by electrospinning technique. So what you see here is a membrane developed from the starch developed from palm kernel shell. It is from empty fruit bunch. So this one is developed as a non-woven fibrous membrane. And one of my former PhD student, Dr. Izan, he is an assistant professor in my university. So he developed a water filter using this membrane. And since electrospinning can produce very low pore diameter fiber, and this is an ultrafiltration membrane which can be used for ultrafiltration purposes. Using this membrane, he developed a portable water filter, which he called PortFilt. And in another development, this starch is added with curcumin. Curcumin is the active ingredient which is and anti-cancer, antibacterial, antiseptic. Curcumin has a lot of medicinal properties, and it is discovered that the turmeric in Kerala has the highest amount of curcumin. So this girl in the right side, she has added some curcumin in the starch, developed a non-woven fibrous film, and used it as a wound dressing medium. And she has shown that when this fibrous scaffold, or when this material is used as a wound dressing medium, the wounds it recovers faster than that doesn't contain curcumin or doesn't contain the natural product. So in all means, we have a water filter that can be fabricated from all renewable sources, and we have a wound dressing medium that can be fabricated from all renewable materials. Here, everything, starch, curcumin, everything is from renewable materials. Continuing with this, one of my previous postdoctoral, Dr. Bhupender Pal, he made a peculiar combination of cellulose derived from empty fruit bunch. He made a composite with polyaniline and reduced graphene oxide. All these materials can be developed from renewable sources. And he showed that he can make a composite which will offer much higher charge storability than any other mixture or any other mixture of this composition. The importance of this composite is one is cellulose, RGO, and panning. This can be developed into flexible fibers and yarns by using techniques like electrospinning. We have recently written a paper regarding this. What are actually the requirement for the fiber electrodes for wearable electrochemical energy storage? So if we use this composite to make a yarn-shaped charge storage device, it can be used as a wearable electrochemical energy storage in your clothes. And that can be used to power a large number of IoT devices. And we have written an article in Energy and Environmental Science, which the current impact factor of this journal is about 33, where we listed what are the precautions we must undertake while developing such kind of fiber-shaped energy storage devices. So another approach where we can use very less amount of materials to fabricate or to develop functional materials is metal organic framework. A lot of areas have shown that metal organic framework work well in a variety of applications with minimum amount of metals. In one of the works done in my laboratory by Ms. Nurul, she is doing her PR doctoral research. She has developed a metal organic framework using terephthalic acid, and she made some 3-4 metal organic frameworks with cobalt, copper, and nickel, and their composites. And she has shown that if she used a peculiar combination of this copper, cobalt, and nickel in this terephthalic acid-based metal organic framework, that composite can be used as a charge storage medium of high efficiency than any other composition, which we published in last year in Industrial and Engineering Chemical Research, published by the American Chemical Society. And very recently, we have shown that the same metal organic framework will work well as a nilutamide sensor. Nilutamide is an anti-cancer drug used to treat for a male-specific cancer, prostate cancer. So this nilutamide is this particular metal organic framework containing this triple component metal-based metal organic framework. It works as a very good nilutamide sensor. We again developed a lithium-ion battery using that. We initially got high specific charge, but the cycling stability is very low. And we are currently studying what are the problems of, or what is actually happening with the cycling stability. We got some positive results how to fix it. The experiments are currently underway. So continuing, these were not the only thing happening in my university. There are a few other examples which I would like to highlight with you is one of my colleagues, Dr. Fatmawati Adam. She has developed a capsule, which is a drug delivery medium. When we make capsules, when we make drugs, we can see drugs inside this capsule. Usually, this capsule is made from an animal protein called, I'm sorry, just forget its name. This capsule is conventionally made from animal protein, and there are a lot of vegetarians, including Muslims, and plenty of vegetarians in India. They are concerned with the source of the material. So what Dr. Fatmawati has done is she developed a carrageenan. Carrageenan is a seaweed, algae, and she toughened with cellulose nanocrystals, which again derived from plants. Seaweed is a very, very soft material that cannot be used to develop capsules. So when she added a little amount of cellulose nanocrystals, it became tough. It got sufficient mechanical strength to develop them as hard capsules, and using which she developed capsules. So we are now selling this technology to a company here in Malaysia. And one another of my colleague, Dr. Nadana Murugiraj, he is working with algae. What he has developed is he has identified a carbon dioxide eating algae. And he further developed to control the parameters such that this algae eat more carbon dioxide and develop a large amount of fatty acids. So, and these fats can be recovered and can be used for many applications in healthcare, food, biofuel, environmental applications, and so on. So plenty of applications, plenty of ways we can look at the natural sources and can further develop them without destroying our ecosystem or mining for metals and metal-based components. So to go to the next part of my talk is big data. Yes, let me introduce that with this figure, where you would see the production line of automobiles with a lot of robots controlling the production line. Probably you could see, if you carefully look at this slide in the left, you would see that there is only one human being there supervising or monitoring what is happening if anything is going wrong. So think about the future of a graduate who got a degree in automobile engineering and hoping to get a job in a automobile production plant. He's not required, because these machines can work 24 hours in a day and 7 days in a week. It will work, no complaint, and its only food is, other than tearing off its parts, only food is electricity. As long as we are providing it, it works. That's not the case with human. So the emergence of these kind of technologies, what's called the disruptive technologies, that will take our jobs away. So how do we train our students so that they are relevant and sustain in the future job market? One very good example for disruptive technology is in the right side, which we know. Uber started from Uber. I think in India it is Ola, and in Malaysia it is mostly gram, and there are in many parts of the world they have different software platforms. So we have seen how Uber, Ola has destroyed the taxi driver's job. When it destroyed the taxi driver's job, it created numerous drivers' jobs. So anybody can be a driver now if they want extra money. So this Dell Technologies, that's a organization in the United States, they estimate that around 85% of the jobs that today's learners will be doing in 2030 haven't been invented yet. So how do we train our students in this rapidly changing scenario of technological evolution is the big question now, and how, as material scientists working in the laboratory, how do we approach the materials research from now onwards? What is shown in this slide is our conventional way of materials research. We have recently, in collaboration with a top professor in the National University of Singapore, we wrote a paper 2 years ago regarding this topic. So how do we do materials research at present? At present, we conceive an idea and we go to laboratory, do systematic experimentation. At the end of the experimentation, either we prove our hypothesis or disprove it. If we prove our hypothesis, we go on to make a prototype and test it in the real working environment conditions. And if this prototype works well in the real environment, the next stage is the life cycle assessment, where most of my technologies fails, where they see the sustainability of these products in the market and issues like price and carbon load. If all these things means an idea can lead to a product that can be manufactured at low costs, and the products do not support or do not cause high carbon dioxide emission, then we can deliver this idea to manufacturing sector. This is actually the current way of technology development. And do you know how long it takes from ideation to manufacturing? It takes about 20 to 30 years for an idea to be delivered into the manufacturing sector. And do we have that kind of time? And you would see that it's a very, very inefficient procedure. And that's why most of our people working hard in the lab, they never contribute a product, high-end, high technology or highly engineered products. It very hardly come out from the university or research laboratories, because the process is very inefficient. We call that as materials 2.0 in analogy with Industrial Revolution 2.0. The next stage of material research is engaging theoretical material science, like computational material science. I have seen Dr. Suresh from RL also among the audience, and he has been doing it, computational material science, where we can design a material of target functionality using materials theories. So that's quite easy, or not easy. It requires a lot of computational time, but it doesn't require much chemicals. It doesn't waste much chemicals to do trial and error experimentation. The experiments are done by calculation, by solving Schrodinger equations or other material theories, and tell us that this is the material that you are looking for, having these kind of properties. And if we identify that kind of material, then we go to lab to test it. Even though we have to follow that conventional procedure, this process of engaging materials theories and computational materials into the material discovery is really a higher end than the materials 2.0. And that's why we call this process as materials 3.0. And this is at a higher competency level. Into this, just an example that has done in my laboratory, where Dr. Amina, she has graduated with this work, where she designs new molecules that can be used as a photoacoustic imaging medium to image our internal organs. So she used density functional theory calculations to design these molecules. And then once she has the material, she went to laboratory and synthesized them and shown them that there is a systematic variation in the photoacoustic emission as predicted by her calculations. And some of them showed the highest photoacoustic intensity so far. So this process, again, we need to go through the rest of the stages. This paper is just now accepted in Journal of Materials Chemistry. So the reason why I'm telling all this case is really summarized in this slide. So when you look at this slide, you see certain statistics. According to World Bank, 1 in 1,000 people in the world is a researcher. And according to the scientific database Scopus, a research paper is published in 20 seconds. So by the time I complete my lecture of this 1 hour, how many papers would have been, hundreds of papers would have been published in so many areas. I listed few cases here, for example, sensors. These are the number of papers published every year with the keyword sensor. You would see that every single year, nearly 100,000 or more than 50 or 60,000 papers being published with the keyword sensors. What about graphene? Graphene has about more than 20,000 papers being published every single year. And what's the case of energy? 200,000 papers is published every single year on energy materials. So if you want to find out what's actually happened in the case of sensors or graphene, can we read at least the paper published in a single year and come to a conclusion? And probably the questions that we are looking for is already answered in these answers, in these papers. All these research papers are available in machine readable form. So how can we train a computer, or how can we generate an algorithm to read all these papers and answer our questions? That's what the next stage of material research means, that there is a big data existing on material research or materials data on structure property correlations, composition property correlations, and processing property correlations using variety of methods like multi-scale modeling, materials theories, and so on. So if we engage this computational platform to answer our queries on materials related issues, we train a program to learn from this existing data and answer our queries. For example, what are the characteristics of an energy storage material to have an energy density something like 1,000 watt-hour per kilogram and power capability 10,000 watt per kilogram? Then probably the answer is there. There, we need to have this data analytics and engage programs like machine learning, deep learning, multi-scale modeling. And this current level of computational theories, materials theory, allow us to fabricate or develop conditions for material synthesis and manufacturing in a computational platform. Means we really do not have to go to the lab and test, synthesize, or find out the route for synthesizing this material. We can do it computationally. And once we have the right materials, then the next issue is prototyping. Prototyping, testing, and validation, all these things can be done in the computational platform. The next issue is life cycle assessment. All these things can be done in a computational platform. We call this process, in analogy with Industry 4.0, as Materials 4.0. It is not a scientific fancy. Many laboratories started working on that. Mostly, it started in the United States after President Obama started this program on materials genomics in 2012, I think. After that, they started working on computation, or means accelerating materials discovery using computational platform. If we engage this one, if we efficiently find out what is actually the method of doing this, still the world is on the learning curve how to do this. Nobody knows it exactly. Many papers are published, and if we can invest our intellectual input in this scenario, most likely we can accelerate materials discovery. For example, how to recycle single-use plastic. That's a question the world is badly looking for. And a lot of investment has been done. Now, still there is no solution. So if we use this, probably we can get a quick solution. So that's we call the Materials 4.0. And towards the end of this lecture, the last part is the circular economy of this one. I don't know how many of you have heard of this term, circular economy. To understand that, we first understand what is linear economy means. Linear economy, according to that model, we make products, we use them, and we dispose them. And what happens with the disposal? We pile up waste. There are two images shown here. The right side is the plastic waste accumulated in the Pacific Ocean, whose size is similar to the size of India in the Pacific Ocean. And thus that can cause, or that is causing, huge environmental threats. And on the coming years, this threat will propagate, and we are going to face it in a more bad condition. And in the left, you can see the waste piling up. And in India, the waste management, and especially where this, the city where Marvanias College is situated, in Trivandrum, one of the big threat there is waste management. While I was a doctoral student at the Council of Scientific and Industrial Research, I would really see could not pass through that some of the roads without my nose open. That's the case there. So how do we solve this one? In the case, so we will never solve this issue unless we see this waste as resources. So how to do this is what's called the circular economy. In the circular economic model, we make products. There are two circles there. The inner circle is the circular economy model, where we produce, the products are produced at the company, and once it is distributed and we purchase it. And the next part is by the consumers, consumption and use. Yeah, we consume that. And what after consumption? In the linear economy, we throw away. And in the circular economy, all these waste are collected, extract every component of the used product and fed back to the production line. Every single atom in a material used product is detached, recovered, and fed back to production. And this is called the circular economy. The way and how can it help the future is in the outer circle. It simply says how or what are the job creation status using circular economy. So you can refer this: designing, reducing process reduction, collection, investment in infrastructure, all these things will make a lot of jobs when we start engaging and employing circular economy in our society, where we extract all useful components from a used product and fed back to production. So waste are many. These are few examples. For example, in Malaysia, nearly 15,000 tons of leftover food is thrown every single day, including 3,000 tons of food that is still good to consume. How bad this situation when realizing that there are certain parts of the world where children and people are starving for food. So all these leftover and thrown away food contains plenty of nutrients. And how do we extract them? Engaging the model of circular economy. And the next one is electronic waste. This recycling of electronic waste is actually started doing in India. One of my friend's laboratory, Dr. Ritesh, is laboratory. He directs Center for Materials for Electronic Technology, CMET, in Hyderabad. He is directing that institute. They actually started doing recycling electronic waste. So what promise it gives is, I can tell you in a simple example. When you process 1 kilogram of gold ore to get 1 gram of gold, you actually, if you process 1 kilogram of electronic waste, you can get 4 grams of gold. So that is more profitable and efficient. We get more gold from electronic waste rather than we go for mining. So there are plenty of electronic waste. About 50 million tons of electronic waste is produced every year. And from 50 million tons, you can calculate how many grams of gold can be extracted if you develop technologies efficiently to extract them. So in our laboratory, we did some small work. We have converted the used tissues into porous carbon using some protocols, which I did not include here. So what we have done is we process this waste tissue. In fact, they are laboratory waste. These laboratory waste tissues to get cellulose from it. And that cellulose is developed into carbon. And we developed an energy storage device. And we have shown that the energy storage device perform well. Again, this work is currently under patenting and publication. So there are opportunities around us how to locate waste and what are the useful component of it, what are their selling, the active materials in it, how do we extract them. So those are the case. So let me make some predictions here for the future of employability. I would feel that the future of employability for material scientists, this will depends on 3 major technologies. One is artificial intelligence, like machine learning, deep learning protocols. Next is blockchain. Blockchain is actually encrypting the history of production to the product. And the third is the circular economy. So the way we manufacture products, currently it is moving from in the 3rd industrial revolution to 4th industrial revolution. Probably it will move from 4th industrial revolution to 5th industrial revolution soon. But whatever be the method of production of the products are to be manufactured from its raw materials. And as material scientists, we need to find out the source of them. So that's the case. This is a concluding slide. Just to give you some statistics, there are 3 examples there. The first column is the evolution of industrial revolutions. The first industrial revolution, where the manufacturing is enabled by water and steam-powered engine. It happened at 18th century. The second industrial revolution happened the early part of the 20th century, means two centuries later, where the production line started engaging electricity from steam power to electricity in early part of 20th century. And the third industrial revolution, which started engaging the electronic components and robots in the production line, that happens 60 to 70 years after the second industrial revolution. And the fourth industrial revolution happened much quicker, means now, in 50 years. The next column shows the increase in population. In the year 1804, there was only 1 billion population. And in the year 1927, the population is doubled. And it took 123 years for the population to get doubled. The third billion is added relatively quickly in 32 years. The fourth billion even quicker in 15 years. The next billion even quicker in 13 years. Currently, a new billion population is added in 10 to 15 years' time. The third one is some other statistics on reaching a technology to its consumers. Telephone took 25 years to reach 10 million customers. And World Wide Web Internet, it took 7 years to reach 100 million customers. Facebook did it in 4 years, Instagram did it in 2 years, and Pokemon Go did it in 1 year. The message today is changes are rapid in the current world, and the ability to quickly change is the key to survive. And thank you for your attention. These are some of my funders. Noritake is a Japanese company, and most of my research money is coming from Ministry of Education, Malaysia, and my own university, in addition to some research money from a private university in Taiwan, Minchi University of Technology. And then thank you for my team, Nanostructure Renewable Energy Materials, UMP. And thank you for your attention. Thank you very much.
Can you hear?
Hi.
Sir, we are here. We have some doubts from the students or the participants.
Yeah, please go ahead.
So,
can I switch on my live, please? Give me a moment.
Yeah. Dear participants, if you have some doubts, please write it in the chat box. Again, dear participants, if you have some doubts, please write it in your chat box. And please your mics switch off. Sir, I have one question got.
Yeah, please go ahead.
How about the stability of the carbon materials that you developed under reducing atmospheres?
Yeah, that's a good question. This carbon from bioresources, that strongly depends on from where it is developed, because the quality of natural product depends on the soil. I think, as I mentioned, the curcumin, the turmeric in Kerala has the highest amount of curcumin. Why is it so? Some active ingredients is high there. So what I want to say is, different products, different agricultural products developed in different parts will have different materials components. And for electronic application, oxygen is a very bad component. And if high electrical conductivity is required, oxygen deteriorates. And if there is one of the ways to get rid of the oxygen is heating them in reduced environment. So we have to reduce it. So far, stability-wise, there is no issue with the stability. We have heated these materials up to 900 degrees Celsius in argon and nitrogen environment to develop purely oxygen-free carbon. They work well, but probably everybody have to look at the chemical composition of their resource, raw material, before planning a heat treatment. But in terms of stability base, there is no issue.
Okay. Thank you, sir. There is another question. And how did you study the hydrogen storage property of the metal oxide coated carbon, or the hydrogen
no. In fact, no. One of my collaborating laboratory in Tokyo Technological Institute, they have done some preliminary work for making a hydrogen evolution reaction using this material, and they have promising results, but still a lot has to be done. But in terms of carbon storage, hydrogen storage, we did not use it.
Sir, there is a question from a first-year graduate student.
Okay.
What is the activated carbon, and can you please explain its meaning?
Okay, fantastic. So activation means when you carbonize, when you heat, or look at, probably the student is from Kerala, when you heat or when you burn a coconut shell, you get carbon. But that carbon is highly dense. It doesn't have much pores to accommodate charges. And most of this energy storage is by storing charges. So where the charges are stored is in its pores. So when the surface do not have that kind of, or that many pores, that material cannot store much charge. So developing the pores is actually the activation. For that, what we do is erosion. Treat this carbon with a highly erosive material. It can be done in different ways. One is chemical method, like some erosion like potassium hydroxide or zinc chloride or nitric acid. When we reflect this carbon using any of these, or more than that, the list is actually much larger than this. When we do that kind of treatment, there is erosion of materials from the surface, and we get when the surface becomes irregular, the area becomes higher, and we will have a large amount of pores there. Making additional pores in a carbon surface is called activation. If you don't activate it, that's normal carbon, just like your burnt coconut shell. The other method of activation is physical activation, something like steam. Use a high pressure steam to flow through this carbon. They make enough number of pores. These are the two methods.
Okay, sir, thank you. There is another interesting question, and it's really tricky. Why you avoided silver and used cobalt for coating your carbon?
Yeah, good question. It's actually, let me say the history so that you will understand. We did two experiments there. One is manganese oxide coating and cobalt coating. So the process was same. We mix cobalt acetate or manganese acetate with carbon, palm kernel shell carbon, and then heated at 700 degrees Celsius. So the precursor cobalt oxide can be reduced at 400 degrees Celsius. So we get metallic cobalt. Whereas for reduction of manganese into pure manganese oxide into manganese acetate into manganese, it requires much more temperature than 700 degrees Celsius. So we did not get pure manganese. So the case is, it's a choice. We did not use silver. You can use it. Yeah, that's it.
Thank you, sir. And another question is, sir, how can we extract gold from e-waste?
Okay. The current method is very, very inefficient. Is by leaching. So use mineral acids to leach or dissolve the components and then selectively crystallize. But there are so many metallurgical and chemical processes to metal extraction, similar metallurgical process. But the issue is leaching need a large volume of organic and inorganic solvents. So if you use those quantities of solvent, it will pollute the environment. That's where we need new protocols like machine learning or artificial intelligence, which is the best way to recycle an electronic waste. Currently, it is done using leaching. People are searching for alternative methods. So far, there is no, or I did not have seen any promising results on extracting gold or any other useful component other than leaching. But I'm confident that by engaging this material 4.0, we can get this extraction process easier.
Okay. Sir, there is one more question from a first-year graduate student. That's interesting.
Yeah, please.
You used cellulose nanocrystals
Yeah.
to producing capsules, yeah?
Yes, exactly.
Replace these kind of things instead of plastics, or like,
Good question. Excellent. One direct answer is plastic cannot be digested in human body. So it will create problems in your body. The next thing, the way it can be seen is, actually people have powdered plastics and mixed it with bitumen. Bitumen is the material that we use for tarring. So that powdered, powdered plastic is added in bitumen and used for tarring, and that roads are very durable. So the direct answer for that is plastic cannot be digested by human body. And yes, please.
Maybe she is asking the other way, like can we replace plastics by this kind of cellulose nanocrystals or something like that? For
plastic means not directly it is, because it cannot be for medical applications or bio applications. We cannot use plastic directly because it cannot be digested. On the other hand, if you develop a protocol that it can disintegrate, it's fine. So what is that protocol? That's the question. So that's where the brilliant younger minds have to invest their curiosity and intelligence. Yes.
The fresh ideas always comes from a fresh mind.
Yes, exactly.
So I know that we are running out of time, and one last interesting question for you is that is there any research going on surface science to reduce the life of coronavirus in your laboratory?
In our laboratory, we don't have, but one of my colleagues was successful in genomics, in sequencing this gene in Malaysia. He is first to do in Malaysia, and that was done in my university and in my department. But very bright minds with much better infrastructure is on that. We are not doing it.
This is from the question answer side, and thanks for answering the questions.
Yeah, thank you for your attention too. Thank you very much.
Hello. To propose the vote of thanks, I invite Dr. Sumabai, faculty member of the Department of Physics.
Hello. Good evening, all. Thank you so much for this great opportunity. I'm Dr. Sumabai from Department of Physics, Marvinus College. It was a wonderful session. Professor Rajan Jose gave us a great insight on the topics such as smart sustainability, renewable materials, nanowires, solar cells, supercapacitors, and their various applications. He also elaborated beautifully that materials are the index of human progress and its impact on circular economy as well. On behalf of the Department of Physics, Marvinus College, and also on behalf of all the participants of this webinar, I express my sincere gratitude to Professor Rajan Jose. Thank you very much, sir.
Thank you, madam. Thank you very much.
Okay. We are also grateful to all the participants who have attended this webinar. Thank you all. We will meet tomorrow at the same time. Have a nice day.